that we have to cover today. It's
Mm-hmm.
basically what this picture is showing, that machine learning field has been divided into four kinds of learning. Supervised
Mm.
learning is that you have labeled data set. Labeled data set meaning
Mm.
you know what you have to figure out. Like you have image classification problem of differentiating between a cat image and a dog image. So the data set which is provided to you, it has got labels also, that it is telling you which images of cat and which images of dog, and then you can test it also.
Okay.
And unsupervised learning, you don't have labels, you don't know if what you're predicting is
Mm-hmm.
correct or incorrect. You simply have to
Okay.
trust the domain experts and trust your gut about what, like outlier detection and clustering. Two examples have been given here. Then there is third
Which
field.
one? Outlier detection.
Yeah, outlier detection is unsupervised learning, because you
Okay.
don't you never in outlier detection you don't have labeled data, and it then there is semi supervised learning, that in that you have its novelty detection. For example, when at the time of training you define an area that my good data points lie in inside of this boundary, and anything
Mm.
outside of this boundary would be a novelty. So you know what right data point, what a right data point looks like, and
Mm.
anything new that you see, you simply say that I do not recognize this and this is a novelty. This is semi supervised learning. And
Mm.
then there is reinforcement learning, where there is a concept of reward and penalty, that you take a step, and if that step helps you progress, you get reward. And if that step, like touching an iron hot object in real world, we learn through, we don't have to actually touch it, but if you touch a hot object, you get penalty, and you remember that touching hot objects reduces your life score, and just like and doing something good that benefits you gives you reward. So that is the concept of reinforcement learning. So these are four fields. So decision tree learning comes under supervised learning. We would have labeled data, and we try to
Mm.
predict what a label for for unknown data. Now decision tree learning is, we have discussed that we will have label training tuples. So a decision tree is like a flow chart, tree structure. Then there are internal nodes, denotes a test on an attribute. Each branch represents an outcome of the test, and each leaf node, terminal node, holds a class label. The topmost node of a tree is called a root node as usual. This is the data set where we will predict whether.
Are you sharing a screen? Sorry, Ashish.
Okay, I yeah, 1 second. It happened by
I am
mistake.
unable to see your screen.
Yeah,
Yes.
yeah, yeah, yeah. Thank you for it happened by mistake. 1 second.
Mhm. No problem.
This is what we spoke about in the previous minute, where I was talking about four kinds of learnings and the
Mm.
examples of them. Decision tree comes under supervised learning, and
Supervised means it will have certain already some data set will be available which can be
yes,
used
which
to
is
detect the
labeled,
another data set.
labeled data. That means you know, if like a cat and dog image classification
Mm-hmm.
problem, the data provided to you, you already know what that image is of. So you don't, at the time of testing, it helps you that you can get an accuracy score, and all of those things come into play, that you can calculate your accuracy. But for clustering, you cannot calculate your accuracy, right? You only know that it is your gut that tells you whether there are 3 clusters or 4 clusters, there is statistics, there lies statistics behind it, like that elbow curve, and we would discuss that topic in a different session. But right now, by supervised learning, it means we have labeled data. By unsupervised learning, we have we don't have labels. And semi-supervised learning means we have labels at the training time, but at the prediction time, we do not have labels. And reinforcement learning depends upon the ideas of reward and penalty.
Okay, so reward and penalty, you mean to say?
That if you take a good step, you get rewarded. If you take a bad step, the wrong step, you get penalty and penalized, and you get a penalty, and you remember that, and then you proceed further in solving the problem.
Okay.
So,
and what is that clustering and outline detection?
Clustering and outlier detection are examples of unsupervised learning.
Means not able. Clustering means you are clustering a set of data, is it like that?
Sorry, what?
No, is it some cluster of data? Clustering means suppose you are segregating one set of data from.
So, for example, you have t-shirt sizes, and you have to separate them on the basis of t-shirt sizes. You have to predict how many, what is the best way to cluster t-shirts into categories so that they can be sold out to the market in general. Like we have certain sizes like small, large, medium, small, large, extra large. So that kind of that is the problem of clustering, where you try to group the data into which look familiar.
Okay, it means different segments, like small, large, small, medium, large, extra large.
Yes. So clustering is an unsupervised learning, means you do not already know how many segments will be there, how many clusters will be there. And that you also have to decide. Now,
an outlier detection. Outlier
detection is that, for example, some transactions are happening in with a credit card, and let's say at a specific day you make a transactions of hundreds and thousands, but somehow on a given day a transaction happens which of the order of 100,000. Now that is an outlier, because till now you have been seeing some transactions like 100,000. Now 100,000 is a very big number, and that will stand outside of the regular data points which you have been seeing in your transaction data till now. So so this is a very basic example of outlier detection. And moving on to decision tree. With decision tree learning, you will have labeled data. So each internal node.
And novelty. Yeah, sorry, Ashish. Yeah, novelty and this one. Can you please also say semi-super?
Yeah, novelty detection is something different. In novelty detection, you do not you know what right data looks like. You say that, okay, this is the decision boundary. Let's say I have a circle, and every data point lies inside the circle. Now as the time passes by, you see that a point appears outside of the circle. So now you figure out what to do with it. Now this problem of figuring out that we have to during the training time, we know what the boundary is, and when the model is deployed, it tells you that if a point lies outside the circle, you just highlight it as a novelty. So it's like change in the data set. Some data points are differing on one or the other attributes, and you have not seen such a data point before. So that is a novelty.
Okay. All right, and the last one is this one.
This is an swarm intelligence. Swarm intelligence is like you have ant colony, right? Ant colony learns by mistakes of the individual ants, because if you are familiar with the biology of ants, if when an ant dies, it releases some smell in the air which helps other ants know that there is danger in that path. So entire colony has an intelligence of its own, and it moves away from that region where an ant has died, because when an ant dies, it releases some kind of smell which indicates to the other ants that there is danger in that area.
Oh, okay.
So
Okay,
this is like,
fine.
yeah, and
Means some kind of intelligence which the ants are trying to
swarm,
pull it.
basically reinforcement learning. It's based on the ideas of reward and penalty. If you take a good step, you get rewarded. If you take a wrong step, you get penalty. Like a child who touches a hot object learns that immediately, he retracts his hand and he does not have to process it, that he does not have to touch a hot object, but he get penalized for touching a hot object. He or she get penalized for touching a hot object, and that is reinforcement learning, that you should stay away from these electrical sockets and stay away from. So this is an example of reinforcement learning in real life.
Okay, yeah, thank you.
Now decision tree induction is that when what composes a decision tree? A decision tree is a flowchart like tree structure. Each internal node denotes a test, and each branch represents an outcome of the test. Each leaf node holds a class label, and the topmost node is the root node. That is how we interpret a decision tree. Now, this is the data set where we are going to predict if a person whose age, income, student, and credit rating we know about that person. We are going to predict whether or not the person buys a computer.
Okay.
So then we raise a question: is this what we want? Do we want to start building a decision tree based on age, and then we check if the person is a student or not, and we want to check. Now, now this has been shown to you already, but basically we would explain in the following slides how do we understand which attribute to select to decide to begin splitting the data and consider as a root. Now, attribute selection measures. Information gain, entropy is one of the way to do attribute selection. Then there is gain ratio, and then there is Gini index. In information gain,
so these parameters are used for your sorry for interruption. So information gain ratio, Gini index. So these are the parameters to detect or find out the decision tree.
Find out which attribute is best to split the data. So when you have age, when you have age, you can split the data into youth, middle-aged, and senior. Right? If you move the credit rating at the top, that will have like whether the person has excellent credit rating or fair credit rating. So we are going to, a decision tree helps you split the data and then decide, you move along that path and decide whether or not the person buys a computer.
Okay. With a student is the correct or your youth, they are youth or not, or if there is a credit rating they have, or if they are middle-aged or not. So these are the parameters which we'll be detecting using these three options. Is my understanding correct?
Yes. So we have these attributes: age, income, student, and credit rating here over here. So we are using them to build a decision tree. Income is not there, but income will also come into picture. We'll figure that out also. In this screen right now, that you are seeing right now, information for a tuple in the data set expected information needed to classify a tuple in dataset D is given by this formula, where pi is the probability, and then we take the logarithm base 2 of the probability, and then we sum over all of those terms. It's a summation of all the probabilities of seeing an arbitrarily tuple in dataset D that belongs to class C1 Ci, and the probability is that all the tuples belonging to that class divided by D. So we'd walk through an example. Now we have information.
Yeah.
Now over here we have the class By's computer has yes and no. How many no are there? 1, 2, 3, 4, 5. 5 no are there. And if 14 is the total number of how many yes are there? 1, 2, 3, 4, 5, 6,
1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9.
Yeah. Now, how do we calculate how much information is there in this data set? Now, if we use the formula, we'll say 9 by 14 and logarithm of 9 by 14 for all the classes. Yes and no are two classes we have. Then for class yes, we put the probabilities and the numbers into the formula and get that information in the data set is of 0.940 bits. Information required to encode this data is 0.94 bits.
So these are log value. There are log tables, I think from there we'll get it, right?
Yes. Or you can use
minus
calculators.
Okay, using calculator also, I think it is possible.
You can get, so in the algorithms, this happens automatically. We'll discuss code tomorrow or a day later. Right now, we are discussing the theory. Now, information gain when we split on age. Now, what happens when we split the data based on age? Now, over here, you see that information in the dataset D is of 0.940 bits. Then we split on age. This is the formula for calculating information when the data is split on age. Number of data points belonging to that to a class, because age has youth, middle age, senior. Then if you see how many youth are there, age 1, 2, 3, 4, 5. Youth are 5. Middle aged are 1, 2, 3, 4. Middle aged are 4. Youth are 4, and senior should be 5. 1, 2, 3.
Senior
4, 5.
1, 2, 3, 4, 5. Yeah, 5 are there.
5 senior, 5 youth, and 4. So this is the. Now, how do we do that? Now, this is a weighted summation of information for any particular value of the attribute. When age is youth, we calculate information, and it is a weighted sum. That means we multiply it with number of instances of that attribute's value. Like youth, we had 5. Middle age, we had 4. Middle age, we had 4. Senior, we had 5. But then we are also multiplying it with the information in that segment, with youth information in the dataset. When we know that the person is a youth, person is a middle-aged person, and person is a senior person. This is basically. So getting this, how this equation has been written, or shall I?
No, equation means all 3 parameters. It has 2 parameters. It has taken. Is it means the senior, then your
middle age and youth, middle age and senior.
Correct. So there should 3 terms should come up, right, instead of 2.
No, there are 3 terms. This is first term, this is second term, this is third term.
Okay, okay. And what is 5? Oh, 5 by 14 means out of 14, 5
Wait,
are
wait.
suppose youth.
This is a weighted summation, so we weight
Okay.
each term is weighted by how much how much based on the concentration, based on number of youth that are there, number of middle-aged people that are there, and number of senior people that are there. So this is a weighted sum, and 5 comes from the fact that there are 5 youth. 4 comes from the fact that there are 4 middle-aged people, and then 5 again comes from the fact that there are 5 senior people.
Yeah, no, these numbers I got it from the table, whatever the data set is there. But regarding the formula, how we are implementing that part only I have. So
Implementation we'll discuss at a later point of time, but you have to remember that when
okay.
when information gain, when we split on an attribute, for that we do a weighted sum, and when we have also when we are calculating the information number of bits required to encode a data set, that is also a weighted that is a summation of probability of each class multiplied by logarithm of probability, log base 2 probability of class I. So these are two formula: information of number of bits required to encode the information in dataset D, and number of what information you gain when you split the data on an attribute on a feature. Any questions?
No, that is fine. I just got at a high level that yes, it will be a distributed summation of that info AD means the complete information on the age distribution, right? Is summation of JI to V DJ by D into info DJ. So info DJ is the information on the data set, right?
Yeah,
Means how much percentage?
data set when A is equal to J, when age is equal A, so when weird age is equal to youth, age is equal to middle age is equal to senior, like that.
Correct. But here log you are not using, but in the formula how it log is coming means you are just putting
Info, right?
exact value. Okay.
Info.
Not info, the previous parameter, the summation of j equals to 1 to v.
Yeah, this one.
First term. After equal to first term.
This is summation of dj over d. This is the weight given to each information component.
No, my question is how that log is coming here in the first information.
That is, you have confusion with the formula.
Okay.
So this is the
Okay,
formula
input
for
is P1. Okay. That
pi
means
pi
P1
pi pi pi
PI log PI 2.
pi
Okay.
log pi. Pi logarithm of pi, summation of pi multiplied by logarithm of pi.
Okay.
Then when we have to compute how much information we gain when we split on age, we subtract the information of a number of bits required to encode data D minus information when we split on information required to encode when we have split the data based on age. So 0.940 minus 0.694 gives you this. This is the gain.
Okay.
Then
So the first parameter you got it from where? First parameter NDD. Second parameter I got it, that info HD. The first parameter you got it from the initial option. Can you please show it once?
Yeah. So this is
From
the class, right? You have some yeses, you have some no's. So you each yes and each, so you have two classes. You have a class yes, you have a class no. Now when you have two classes, what you do, you have 9 values for yes and 5 values for no. Then what you do is the probability you find out the number of number of values for a particular class minus the total values in the universe. So 9 divided by 14 gives the probability of that the tuple you are going to pick out from the data set is going to be yes, and the probability that a tuple, randomly picked tuple, will be a no is 5 by 14. So you have minus 9 by 14 multiplied by logarithm of 9 by 14 minus 5 by 14 logarithm of 5 by 14.
Okay.
Okay. Shall we move further? These two formulas are the entire. If you have got the complete understanding of these two formulas, information of how do we calculate the information present in the data, entire data, and how much information is there when we have splitted the data in or based on an attribute. These two formula, if you remember, you compute the gain on doing a split, and then whichever attribute is giving you the maximum gain, you pick that attribute. This is the entire internal working of a decision tree. Now you can change the attribute selection metric, but that is not of very much that we do for theory purpose. But practically speaking, it's good enough if you understand one of these three parameters, three attribute selection measures. So in entropy we have discussed. Now we discuss Gini index. Now Gini index is Gini index is
So the first formula is for entropy, is it?
yes,
Sorry for the interruption. Yeah.
information gain or entropy.
Okay.
Okay. Information gain or entropy. Then there is Gini index. And formula for Gini index is this. If we do a binary split on attribute A, then you partition the dataset into D1 and D2, and this is again a weighted sum expression. If you remember from previous slide, that your Gini of data D1, Gini of data partition D2, weighted by how much tuples are there in partition D2 over number of tuples in the entire data set. So this formula gives you this is a weighted sum of Gini of each partition, and this is Gini index measures the impurity of data D, a data partition or a set of training tuples. And then how do we calculate Gini of data D? 1 minus summation of probability squared. So this is, you have to interpret it in a reverse order. Earlier we were predicting how much gain we have. Now we're predicting impurity, and impurity, you have to select the attribute where Gini is minimum. Do you have any questions in this image? Any questions in this image? This is about Gini. It's all formula based. Are you with me?
Yeah. Sorry, I was on mute. So yeah, this Gini split, what these two formulas is a binary split on A portions. Okay.
yeah.
Into D1 and D2, Gini index given. Okay. Gini index measures the impurity of D and the data partition on a set of training tuples. Okay.
Shall we move on?
Yes. Let's quickly move on because I also have another 10 minutes. In 10 minutes, it should be done, right?
Yeah, this is complete. If you know how to calculate the Gini on dataset, over here we have a subset income we were discussing earlier, right? Income is you have low, medium,
Correct.
high. Now we split the data into two sections. One is that income is high and income is not high. Not high meaning it's either low or medium. That's clear.
Correct.
So we will split the data into two categories, whether the income is high or not high. So high, how many tuples we have when the income is high? 1, 2, 3, and 4. And then 14 minus 4 is 10. So low and medium should be 10, not high should be 10. Now this over here is, this is the weighted sum of Gini coefficients of partitions.
Okay. So how we are calculating this? Okay, 10 by 14 means?
10 by 14 is the weighted, this is weighted sum. What you are seeing over
Okay.
here, right? You have Gini coefficients for each partition weighted by what is the representation of D1 in the data set D? What is the representation of D2 in data set D? Getting it? So
Got it. Yeah, it is a weighted sum.
Weighted sum of Gini
that below it is na Gini D 1 minus, and weighted sum is also given 1 minus summation of I1 to M PI.
Probability squares. Probability that of each class I. We have M classes over here, and we go from I equals to 1 to the number of classes that are there, and we calculate probability, squares of probability of each number, and subtract that sum from 1, and then we get the Gini coefficient. But Gini, when we split on an attribute A, the Gini coefficient for that, how much for impurity that remains in the data set after the split, is weighted sum of Gini coefficients for each partition.
Okay.
This is the calculation which is taken from above.
So this you got it from your material, is it? From that
Yes.
Bispilani material. Okay, fine.
Yes. Now this is these are few, how once we have classified this image comes into picture when you have done the classification of your data set. You have created a model using decision tree. Now you have classified the test data. Now how do you check
this classification is for what purpose, Ashish?
Classification is that you have a data set and you want to predict a class for each tuple, and the classes are given to you, that it's a yes or no, it's a cat or dog, it's A or B or C, it's like it could be anything. It could be a t-shirt size, like small, medium, large. Based on it could be any category, like it could be like your loan default, whether you should give a loan to a customer or not, classification into yes or no. So once you do the once you have trained your model, you have to check the accuracy of your model, right? So before you run the model on the data, you have to split your data set into training data set and test data set. Once that split is done, these matrices are computed on the training data set, where you have accuracy is equal to this. This is a very, I tell you in brief that there is a class which is actually positive. Shall we discuss it next time? Measuring classification.
This